let's say Shahar and me, we're gonna talk about, at least from my point of view, quite exciting piece of work. For me, personally exciting because when I initially approached the subject, I didn't have any clue about algebraic geometry and elliptic curves and isogenies. All this abstract math was like a book with 7 seals on it. I didn't want to open Pandora's box. And actually, it turned out that for that piece of work, one can study these notions if one wants, by something that is very easy to understand and very elementary, and that's the circle, and that's what the presentation will be about. But first, let me, just for completeness, talk a little bit about the history, the line of research. I mean, when I talk about regular Starks, I mean univariate Starks, so not something like Binius or Frobenius. Yeah? So it's nothing like multivariate sum check. I'm staying today just in the realm of univariate Starks. So and typically, what do you need for an univariate Stark? You need a finite field. Often you choose a prime field. But there is one specific property that makes the prime useful, and it's called FFT friendliness. And so classical Starks, you could say the space where you place everything, where you place your domain, where you place your trace on the domain, is the line, just depicted. F, the prime field as a line. You have some action on it of symmetry. That's the multiplicative group. It's a smooth group, considering that P minus 1 is so. That means it's FFT friendly. So that's the key ingredient you need to build a Stark, to have a smooth group acting on something. In this case, it's not even worth to think it's a curve. No, it's a line. Yeah. So, and the object you obtain, so you have witness data, you place it on your favorite domain, and you encode it into polynomials. So this is the algebraic objects you work from. Once you have polynomials, you know, polynomial IOP, Schwarz-Zippel, it's always the same. Then, quite recently actually, there was the seminal work of Ben Sassen, Dan Carmon, Swastikoparty, and David Levitt about the ECFFT, the EC Stark. So what they do is, because often in many applications, you would like to work with a prime field where P minus 1 is not smooth, which is not FFT friendly. So what can you do here? And what they do is here, just change the space, just move from the straight line to something that is well studied. It's a curve, it's an elliptic curve that's well studied, it's abstract, even for me still though. But they say, okay, work on an elliptic curve, because if you know from algebraic geometry, that's a group. And you even can there's a rich manifold of curves you can construct sample. And if you do it in the right way, you sample your curve on which you have a subgroup that is exactly that smooth as you wish it should be. And so the whole Stark works over an elliptic curve. It gets a bit abstract. What are the algebraic objects here you encode witness data into? They become rational functions over that curve. That's essentially what you get, but you can argue similar Schwarz-Zippel. There is an ECFFT, and there's a big misconception in the CK community about the ECFFT. It's really as efficient as the ordinary Cooley 2K two-adic FFT. So, but anyway, why is there this misconception? I suppose for the same reason as I also thought, or we at Polygon, we thought, oh no, ECFFT, it's not as efficient. Because it's 2 80 pages of abstract math. Was too much for me. So the question started, at least when I was thinking about in this direction, is can we do with something simpler? And there was even some preliminary work that we published last year. It was called something like Read Solomon Codes over the Circle group, but that already was the pathway to the circle. And then I met Shahar. I fell in love with him, with this guy. And would you like to marry me? So, applause, please. No, unfortunately, he's almost married already. So no luck for me here. So, okay. So, but the full thing was, can we carry the whole abstract math, the whole machinery? Almost nobody is willing to understand to the simple curve, the circle curve, and that brings us to the circle Stark. So it's a simpler construction over. Everybody knows what the unit circle is. I mean, you can grab it, you can turn it around, you can play frisbee with it, or whatever you like, you know? So that's a very simple thing. And if, now it's not p minus 1, if p plus 1 is smooth, it's a power of 2, or it decomposes sufficiently into small factors, then this is a good choice. Because the number of points, we are finite fields. I'm hiding here the details. The number of points is of a quadratic curve is p plus 1. That's not obvious. Look in the paper if you want to see a proof of it. It's elementary, self-contained. It's not difficult, but it's not obvious if you've never seen it before. Okay, so in particular, p plus 1 smooth, the prime that we have in mind, the Polygon, and also at StarkWare, is our favorite prime, which is heaven for us. It's the Mersenne prime M31. Why it's heaven for us? Look at this. It's 2 to the 31 minus 1. And it's even better than 2 if it would be something like 2 to the 32 minus 1, which isn't prime, by the way. Because if you talk to the people that know how to optimize field arithmetics with AVX or neon instruction, vector instruction set on standard CPU architectures, like he knows better, he will talk about it probably. So this is extremely fast. I mean, there is from RISC-0 just some attribution to it. They really moved to a very cool 32-bit field. It's a Babybear prime, which is already quite fast, and we were thinking a lot about, should we choose Babybear? But we managed to do it with something that is even faster. And that's the reason for that work. So it means for MM31, p plus 1 is smooth, so the circle curve is a rich curve, it's a good curve, it's a group, you just rotate by rotation, you know? You take one point, consider its angle, just think of it, don't compute it that way. And Q is another angle, so you make the additions of the angles that gives you the new point here. That's the group operation. It's the same group operation you know from a complex unit circle if people still have some calculus background. So, okay. So, how does it work? It's a regular Stark. Like a regular Stark, there's almost no difference. I already said everything. But just for clarity, let me recap. So your trace domain, that's where you put your data on, is a subgroup on the curve, or a coset of it. Witness data, which is placed on the trace domain, is encoded into polynomials again, and that's a nice feature of the circle group versus the elliptic curve FFT. So you get still bivariate polynomials, but at least polynomials. And you can argue Schwarz-Zippel like the usual concept. You sample a random point. The whole space is the circle curve. You sample it on the circle curve. I have to say here over a sufficiently large extension for soundness. And then you test the constraints at this point. So this is the circle Stark. This is how it works like. And it has two main ingredients. One is the so-called circle FFT, a simplification of the ECFFT for efficient encoding and polynomial arithmetic, and then tightly related per concept the circle phi, a low degree test. So it is again on the circle. This, for just a matter of time, will be only about the circle FFT. And now I hand over to Shahar. He will explain you the circle FFT by means of a very elementary explicit example.
Thank you. Hi there. When I started working with Ulrich, I really enjoyed working with this guy. He's obviously a genius. When he started, he didn't know a lot of algebraic geometry. As opposed to him, I still don't know any algebraic geometry. Okay, so I want to show you guys a concrete example of the circle FFT, just to show you that it's similar to regular FFT. It doesn't use any group operations, just simple field operations. And if you want to implement or do something about it, maybe this could help you. All right. So we are at the circle over the field. The domains we are working on, unlike regular FFT, which is a cyclic group, it's a cyclic group. And this is a generator. It's 2 points, this time two coordinates, x and y. And this is how the domain of size 8 looks like. You can think about it as if it's the unit circle in complex values, like a plus ib, and it's turning around, but it's on the group, circle group. All right. So I want to try to interpolate these values, which means to find some polynomial of total degree, in this case, at most 4, because I have 8 values. That's how it works in circle FFT. So how do I start with finding a polynomial that evaluates to these points? All right. The idea is to do a decomposition almost exactly like in regular FFT. In regular FFT, you're taking a polynomial and you're splitting it to even and odd powers with a very similar formula. Well, this is almost the same. We're splitting it into 2 polynomials of x, and we have this multiplier of y. This formula is really simple for the circle, because if you put xy and another point x minus y into the first equation, you can extract the values of the decomposed polynomials, as you can see there. f0 is just the average, as you can see, for example. We have the point 2 and the point that values to 8, the symmetric one. Their average is 5. So this is going to be an evaluation of the first polynomial, f0. So we do kind of an FFT butterfly on these 2 symmetric points. And the blue polynomial, the blue decomposed, will be the difference, the anti-average divided by the y coordinate, which is a. All right, so we started with these 8 values, and we decomposed them into 2 polynomials, the f0 and f1, which is the averages and the anti-averages. And the polynomials on the right, actually, they are symmetric, so I only need to specify them on the 4 points, and they're polynomials only in x. So if we look at the operations with it, it's just basic field operations. There was no circle operation involved anywhere. It's just taking the average of the values and taking their difference and dividing by this field element A. Okay.
I just would like, at least for me, to clarify something. If you step back here, even and odd, look at this first function. You take a point, you take its opposite point with the same x coordinate. That's the reason why we need to locate the domain. It was slightly shifted. The identity was not sitting here where you would expect it. So you just have the action of the conjugation map, let's call it that way, the involution, which just switches the sign of y. And this involution gives you, the first one doesn't change under involution, it's even. The second one changes the sign under evolution, it's odd. So in this case, it's really fully analog. Sorry to interrupt here, maybe you said it before, but I love you.
It's great. Thank you for the notes and clarification. Okay, so this is how we start the FFT with a decomposition to even and odd polynomials. And these polynomials are now just polynomials in a single variable, which is nice. We can continue from here on only in single variable. So we do this another decomposition again. I'll just show F0, but F1 will go the same decomposition. So in F0, we have a similar decomposition. This time we need to take a point and its antipodal point. As you can see above, we decompose F0 into two polynomials, F00 and F01, which is again the same as even and odd parts. So this time it's almost exactly it's the same, even and odd parts, only in a bit different basis. We'll show later, but yeah, it's taking even and odd coefficients and splitting them. So again, we'll take these 2 points and we take their average and anti-average and split it to left and right, like this. Their average is 6, as you can see, and their anti-average is -1 over the point B. So this way we can decompose it. And now it's a bit weird to see, but this polynomial has a symmetry. So we only need to represent it as 2 points in a smaller domain. The details are details, but basically, once we take out the domain, we get 2 small polynomials on twice less points. Start with 1 polynomial with 4 values, and get the decomposed polynomials, each on 2 values. And we can continue with this decomposition again to take this polynomial that we have 2 values on it, and we decompose it into 2 polynomials of size 1, which is just constants. So let's go over the entire decomposition and see what we actually did. We start with the fxy. We decompose it into 2 polynomials, f of x plus y f1. Decomposed each one into, again, even and odd. And each one of these decomposed again. So what have we got? This is kind of a polynomial. If we expand the terms a bit, we basically get this representation as a polynomial with a different basis. This is the free term. This multiplies 2x squared minus 1 instead of x squared in the line case. But this is still a polynomial of degree at most 3 in x and 1 at y. And substituting the values we just got, this is the start of the polynomial. So again, simple FFT butterflies is the same butterflies as in a regular FFT. The trivial factors are different, the y and x values, and we got this value. So this is the FFT, and phi is almost the same. In phi, you just take the even and odd parts and actually combine them with a random linear combination. All right, so that was the example. Okay, I think unless you have some ending notes, it's time for a Q&A.
Do you love me too?
Great presentation, thank you. I was wondering, when breaking down the, I think it was the third decomposition, there was an operation where the 6 moved 90 degrees. I think on that slide, if you go back, next slide.
Next slide?
Yeah, a couple more. Yeah, here.
To here, right?
I'm sorry, the last slide.
Here.
So where I think it's 25 over 2 and 6. How do we make it so that the decomposition makes 6 and 25 over 2 opposite?
It's 15 over 2.
Or 15 over 2.
How do we make what? Can you repeat?
So in the next slide, the decomposition shows, 6 on the opposite side of the circle.
Yeah, I mean, if you take this polynomial and you put inside, you take f00 at 2x squared minus 1, what 2x squared minus 1 actually does is does a doubling of the point. So this polynomial, when I put in this point, it actually first doubles and evaluates on the next polynomial. And this one, it doubles and goes to the same point and get this polynomial. So this doubling actually does the repetition, basically. Again, so if we had this polynomial, we start with this point and then doubled, we got this. Or if we started with this point and then doubled, we got this again.
Okay, gotcha. Thank you very much.
Sure. Pass the microphone.
Hi, good talk, thanks. How does it compare to doing ECFFT over M31?
You can also do ECFFT over M31. There are curves for that. The difference is a lot of things become a lot simpler here. First, you use polynomials and not rational functions. And also it's easier to choose your domains, I think. Do you want to add something?
Yeah, I mean, you're right. Efficiency is the same. There are some features, just the way how the ECFFT does proofs, for sake of succinctness, I suppose, though it's even an 80 pager. So we can do something, it's just a very subtle technical feature that the circle is globally isomorphic to the projective line. I know that you understand that. So, and therefore you can carry over a lot of explicit results for Reed-Solomon codes over to the circuit. And that helps that we can do batching step Phi directly over the curve itself. So the way we commit here is even much more we used in the univariate regular case. So we extrapolate to some coset domain, double the size, say, and we commit to it, and we do the by value. In the ECFFT, they have a workaround not to work explicitly on that elliptic curve, because the elliptic curve is not isomorphic, has not a global parameterization. And things would get much more difficult just technically. I believe the results are still valid and possible, but technically it becomes much more difficult over the elliptic curve. So this is one extra feature, and this extra feature helps us to even work in some configuration of the Starks which don't target zero knowledge, where we take the trace domain and just extrapolate to another coset of it, which is just, let's say, the complementing coset, so that both together are a subgroup of double the size. And this, especially this situation, would be hard to prove over the ECFFT. So, short story, a slight technical advantage.
These points are making a subgroup, right?
They what?
Like the point that you're doing FFT over them, like
the domain points.
Yeah. Are
the A minus A and B?
Yeah.
This one? Yeah. What about?
So and this 2x squared minus 1 is the basically parallel to addition formula in elliptic curve, basically, right?
Yeah, it comes from the doubling formula. You can think about it as a complex element. If you take A plus IB squared, you get like a squared minus something else, which is also like, it's the same as a cosine of a double angle. You get cosine double angle is 2 cosine squared minus 1. So it's the same here. You get the same thing.
Okay, so I'm just wondering, like, what is what is the fundamental that the circle is not elliptic area, basically? Why is it genus 0, right? And elliptic area is genus 1. Like, what is the fundamental difference between the groups? Like, the coordinate ring that was on the last slide you talked about, where the polynomials actually come from. Before.
The quotient ring where?
The quotient of the. So the place that the polynomial pxy come from.
fxy?
fxy divided by the the equation of the circle. Before.
In the previous slides, in Ulrich's slides.
Okay, the slides are not there.
Which are not here, yeah. This is like the polynomial space. You take just bivalent polynomial and the quotient by x squared plus y squared minus 1, which is the formula. You will have to take a polynomial's modulus, the EC curve on EC, and you have there another group operation, which is the.
So this is a ring, or that was it, yeah. So okay, backward, I think.
That one?
No, after, yeah. Here. Okay. So
yeah,
this is a ring, right? It's not a field.
Right, it's a polynomial ring.
And then if you take the quotient, you add the denominator, then you get a field. But you say you never hit a rational function, right?
Yeah. I mean, one thing, just the classical regular case. You only get polynomials up to some degree bound, some strict degree bound. It's real Solomon code, right? Yeah. It's already also not a field. So the thing here is, looking at the circle in the most natural way involves two coordinates x and y, and therefore, just if you write down polynomials, they're in two variables. Yeah. But it's still univariate because it's a linear, one-dimensional thing, and the relation imposed on a circle, it's that. So algebraically, it means you take the unrestricted polynomial ring in two variables of arbitrary high degree and so on, and then you factor by the relation given over the circle. That's the ideal, the round brackets. So it's still a ring. It's a ring of the FFT produces an elegant subspace of these polynomials, also with some degree bound. And therefore, we can argue Schwarz-Zippel-like. So this degree bound is very important to have a code with good distance.
Yeah, I understand. The problem comes with ECFFT is that when you apply the group operation on the point of the FFT point, like the doubling, exactly, but here you never get into that, right?
The point is exactly, so you could, the short answer is, given the representation of the circle as an affine curve in the plane, the rotation group is an affine group, therefore everything you get by it is polynomials. The complete picture would be, look at the projective closure, and that means you have only poles at the points at infinity. The funny thing is I had a picture here, but I'm not going to find it because I'm going to lose time and I don't want to make delays here. But if you look at this circle curve in a projective closure over even a degree 2 extension is good enough, it looks like the Riemann sphere. You have two poles actually, 2 points at infinity. This was in the beginning very much counterintuitive. And these are fixed points under the rotation action. These are the good points to choose your poles.
Thank you very much. If you have more questions, I guess you guys will still be around. So thank you very much, Ulrich and Shahar.